Somewhere in the cold reaches beyond our sun's embrace, a small machine drifts through darkness older than memory itself. Voyager 1, humanity's first messenger to cross the threshold into interstellar space, continues its silent pilgrimage through a realm where sunlight becomes just another distant star. Launched on September 5, 1977, from Cape Canaveral, this mechanical ambassador has traveled farther from home than any object humanity has ever crafted, carrying with it not just instruments and data collectors, but the accumulated dreams of a species that dared to look beyond its own horizons. The spacecraft weighs barely 800 kilograms, a fragile construction of aluminum and gold, copper wiring, and silicon circuits. Its heart is a radioisotope thermoelectric generator powered by the steady decay of plutonium-238, converting nuclear warmth into electrical current through a process as reliable as atomic disintegration itself. When it left Earth, this generator produced nearly 470 watts of power. Now, decades into its journey, that output has diminished to roughly 249 watts and continues to drop by about 4 watts each year. This gradual dimming mirrors the slow sunset of all explorers who venture too far from home, yet the spacecraft persists, husbanding its dwindling energy with the care of a traveler rationing the last provisions. The cameras that once captured stunning portraits of Jupiter's swirling storms and Saturn's intricate rings have long been switched off. Those instruments served their purpose magnificently, sending back images that reshaped human understanding of the outer planets. But they consume power that the spacecraft can no longer spare. One by one, systems have been deactivated, a careful triage performed across billions of kilometers by engineers who know they're managing not just a mission, but a legacy. The ultraviolet spectrometer fell silent in 2008. The planetary radio astronomy experiment was shut down in 1998. The tape recorder that stored precious data finally stopped in 2007. Each decision to power down an instrument represents a small mourning, a recognition that resources are finite even for a Voyager in the infinite. What remains active tells us about priorities and possibilities. The cosmic ray subsystem still samples the charged particles streaming through space, detecting the boundary where the sun's influence fades into the galaxy's broader currents. The low-energy charged particle instrument continues measuring the plasma environment, distinguishing between solar wind and interstellar medium. The magnetometer tracks magnetic field orientations and strengths. The plasma wave subsystem listens to the electron density oscillations in the space around it. These instruments, still functioning after more than 45 years, represent engineering achievement that transcends their original design specifications by decades. The journey itself reads like an epic written in gravitational assists and orbital mechanics. Voyager 1 encountered Jupiter in March 1979, passing within 278,000 kilometers of the giant planet's cloud tops. The images it returned revealed active volcanism on the moon Io, the first volcanic activity ever observed beyond Earth. Those sulfurous plumes shooting above Io's tortured surface spoke to processes universal in their physics, yet unique in their expression. The spacecraft discovered Jupiter's faint ring system, captured the turbulent complexity of the Great Red Spot in unprecedented detail, and revealed the intricate dance of the Galilean moons around their massive parent. Then came Saturn in November 1980, where Voyager 1 made its closest approach to any planet during its grand tour. The spacecraft passed within 124,000 kilometers of Saturn's cloud tops and within 6,490 kilometers of the moon Titan, that strange world wrapped in orange haze, its surface hidden beneath a nitrogen atmosphere denser than Earth's own. Mission planners had chosen this close encounter with Titan deliberately, accepting that the gravitational deflection required would send Voyager 1 upward out of the ecliptic plane, away from any future planetary encounters. It was a sacrifice made for knowledge, trading the possibility of visiting Uranus and Neptune for an intimate look at a moon that might harbor organic chemistry relevant to life's origins. That gravitational slingshot at Saturn flung Voyager 1 northward relative to the solar system's plane at a velocity exceeding 17 kilometers per second. The spacecraft began climbing above the flat disk where planets orbit, gaining a perspective that no human eye has ever witnessed directly. From this vantage, the solar system would appear increasingly as an edge-on blade of light, the sun a bright point with planets reduced to mathematical positions rather than visible worlds. On February 14, 1990, and at a distance of 6 billion kilometers from Earth, Voyager 1 turned its camera back toward the inner solar system one final time. Among the images captured was one of Earth, a pale blue pixel suspended in a shaft of scattered sunlight, occupying less than a single picture element in the frame. Carl Sagan, reflecting on that image, noted that this small point contains everyone we've ever known, every human who has ever lived, all our triumphs and sufferings compressed into a fragment of light in the cosmic dark. After taking this final family portrait of the solar system, the spacecraft's cameras were powered down permanently, their mission complete, their energy allocation needed elsewhere. The boundary between solar dominion and galactic expanse is not a sharp line, but a turbulent frontier, the heliosphere. That bubble of charged particles streaming outward from the sun at supersonic speeds extends billions of kilometers into space. Where this solar wind finally slows and begins mixing with the interstellar medium creates a shock wave called the termination shock. Voyager 1 crossed this boundary in December 2004 at a distance of 94 astronomical units from the Sun, entering a region called the heliosheath, where solar wind slows and grows turbulent, but hasn't yet fully surrendered to galactic pressure. The spacecraft spent years traversing this boundary region, its instruments detecting strange phenomena that theories had not fully predicted. There were magnetic highways, unexpected channels where charged particles could stream in and out of the heliosphere with unusual ease. The plasma environment fluctuated in ways that suggested complex interactions between two domains of space, each governed by different source regions and physical processes. Then, on August 25, 2012, at a distance of roughly 121 astronomical units from the Sun, Voyager 1's instruments detected a sudden change. The count rate of solar particles dropped dramatically while galactic cosmic rays increased. The plasma density jumped significantly. The spacecraft had crossed the heliopause, the true boundary where interstellar space begins. It became the first human-made object to enter the realm between stars, a region filled with matter ejected from ancient supernovae and winds from countless other stellar systems, a galactic ocean vast beyond comprehension. This transition happened without fanfare from the spacecraft's perspective. No bells rang, no alarms sounded. The instruments simply recorded different values, noting the change in their environment with mechanical objectivity. Yet for humanity, this passage represented something profound. We had extended our reach beyond the Sun's domain, inserting a physical presence into the galaxy itself. Voyager 1 now swims in the same medium that fills the spaces between all stars, breathing the same cosmic wind that bathes every stellar system in our galaxy. The challenges of operating a spacecraft at such distances strain every aspect of mission design and execution. Radio signals from Voyager 1, traveling at the speed of light, take more than 22 hours to reach Earth. Commands sent to the spacecraft require the same amount of time to arrive, meaning that any communication exchange spans nearly 2 full days. If an anomaly occurs, if systems misbehave or instruments detect something unexpected requiring a change in operations, the response must wait across this temporal gulf. The spacecraft must possess enough autonomy to handle immediate problems, enough resilience to survive its own mistakes, enough redundancy to work around failures. The transmitter aboard Voyager 1 broadcasts at 23 watts, barely more power than a refrigerator light bulb. This faint signal must traverse more than 24 billion kilometers of space to reach Earth's receiving antennas. By the time those radio waves arrive, they've spread and weakened to the point where the power collected by the massive deep space network dishes is roughly 1/1000th of a watt. Yet, sophisticated receivers and signal processing algorithms can extract data from this whisper, decoding information that originated in a realm no human will visit for generations if ever. The spacecraft's orientation matters critically. It must keep its high-gain antenna pointed toward Earth to maintain communication, which requires careful management of its attitude control system. Small thrusters fire occasionally to maintain this alignment, correcting for the tiny accumulated errors that would otherwise slowly rotate the craft away from its distant audience. These thrusters were designed for a 4-year mission. They're now firing after more than 45 years in space, using fuel lines and valves that have been exposed to cosmic radiation and extreme cold for longer than most human careers. In 2017, engineers switched to trajectory correction maneuver thrusters that hadn't been used since 1980, finding them still functional after 37 years of dormancy. Such resilience speaks to conservative design, and perhaps to luck, that ineffable quality that separates missions that exceed expectations from those that fall short. Temperature management presents constant challenges. The spacecraft must be kept warm enough that its systems continue functioning, but most heaters were designed assuming power levels the craft no longer enjoys. Engineers have had to shut down heaters in some areas, accepting colder temperatures in non-critical zones to preserve power for essential functions. The cosmic background temperature hovers around 2.7 Kelvin, just above absolute zero. And while the spacecraft doesn't equilibrate fully with this ambient cold due to heat from its radioactive power source, every watt conserved means another year of potential operation. Radiation exposure accumulates relentlessly. Cosmic rays, high-energy particles accelerated by supernovae and other violent cosmic events, constantly bombard the spacecraft. These particles can flip bits in computer memory, degrade electronic components, and slowly damage the physical structure of materials. The spacecraft was not designed with extensive radiation hardening because, at the time of its construction, the radiation environment beyond Saturn remained largely unknown. That it continues functioning despite decades of exposure suggests either that the interstellar radiation environment is less harsh than feared, or that the engineering margins built into the design were more generous than necessary. The onboard computer systems reflect the technology of the mid-1970s. The spacecraft's memory stores mere kilobytes of data, less than a single modern digital photograph. Its processing power would be dwarfed by a digital watch. Yet this ancient computational architecture has proven sufficient for the mission's needs, executing commands reliably, managing data collection and transmission, and maintaining spacecraft health with straightforward logic unburdened by complexity. There's elegance in this simplicity, a reminder that effective solutions need not be elaborate. Mounted to the exterior of Voyager, 1 is the Golden Record, a gold-plated copper phonograph record containing sounds and images selected to represent the diversity of life and culture on Earth. The record includes greetings in 55 languages, spanning cultures and centuries, natural sounds like thunder and birdsong and whale calls, and 116 images depicting mathematical and physical relationships, human anatomy, terrestrial landscapes, and scenes of human life. The record came enclosed in an aluminum cover electroplated with uranium-238, which serves as a radioactive clock. Any civilization finding the record could determine how long it's been traveling by measuring the isotope's decay. This golden record represents an act of cosmic optimism, a message dispatched to an audience that may never exist. It's arriving at a destination that cannot be specified. The odds of another civilization finding this small object drifting through the vast emptiness between stars approach zero in any time frame meaningful to human civilization. Yet the act of creating and sending this message matters beyond the probability of its reception. It represents humanity's desire to communicate, to reach out, to assert that we exist and that our existence carries meaning we hope might resonate with others. The selection of contents for the record sparked debates about what should represent humanity. Should the message acknowledge conflict and suffering, or present only our best aspects? Should it include religious content? How could sounds and images possibly convey the richness of human experience to minds that might process reality in fundamentally different ways? The final selection, curated by a committee chaired by Carl Sagan, chose to present humanity as diverse, creative, and hopeful, emphasizing our capacity for art, science, and connection while acknowledging the complexity of our nature. The record includes Bach's Brandenburg Concerto, Chuck Berry's Johnny B. Good, a Javanese gamelan performance, and a Navajo night chant. It includes the sound of a kiss, a mother's first words to her newborn child, and the roar of a rocket launch. These selections feel simultaneously universal and impossibly specific. Would an alien intelligence recognize us? Would they understand the emotional content of a mother's voice? Would they care? The record makes no assumptions about answers to these questions. It simply presents aspects of what we are, trusting that even incomprehension constitutes a form of meeting. Voyager 1's current trajectory carries it toward a point in the constellation Ophiuchus, in the general direction of the star AC plus 793888. It will pass about 1.6 light-years from this star in approximately 40,000 years, though by then the spacecraft will be long dead, its power source depleted, its instruments silent, its transmitter unable to signal across the void. It will continue coasting through space for millions or billions of years, an artifact that might outlast human civilization itself, might outlast even the species that created it. This longevity transforms Voyager 1 from spacecraft to monument, from scientific instrument to cultural artifact. Long after its mission formally ends, long after the last signal fades into noise and engineers turn their attention to newer projects, this machine will continue existing. It becomes a time capsule, not by design, but by consequence, carrying forward through deep time a snapshot of what humanity was capable of creating in 1977, what we valued enough to send into the cosmos, what messages we chose to broadcast into silence. The silence itself holds meaning. Space operates at scales that diminish human significance to the point of erasure. The distance Voyager 1 has traveled, impressive by any human measure, represents barely a whisper in galactic terms. The spacecraft has traveled roughly 159 astronomical units from the Sun. An astronomical unit equals the average distance between Earth and Sun, about 150 million kilometers. This sounds immense until one considers that the nearest star, Proxima Centauri, lies 268,000 astronomical units away. At Voyager 1's current speed, reaching that nearest stellar neighbor would require more than 70,000 years. The galaxy itself spans 100,000 light-years in diameter and contains between 100 and 400 billion stars. In this context, Voyager 1's journey resembles an ant walking across a single tile in a floor that extends beyond every horizon. Yet this tiny journey matters precisely because it's ours. Humanity crafted this machine from materials refined from Earth's crust, assembled it with hands and minds that evolved on this planet, and launched it using principles discovered through centuries of accumulated observation and reasoning. Every component, every line of code, every decision about trajectory and instrumentation reflects human choices, human values, human imagination. The spacecraft carries humanity's signature written in aluminum and silicon, in radio waves and trajectory, in the very act of sending something beyond our immediate reach simply to learn what lies there. The scientists and engineers who designed and built Voyager 1 are aging now, many retired, some passed away. A new generation has taken over mission operations, learning from documentation and from the oral tradition passed down by their predecessors. These younger team members must understand systems designed before their birth, maintain relationships with a machine that predates their careers, and make decisions about conserving resources aboard a spacecraft that grows more fragile each year. They've become caretakers of legacy, stewards of a mission that has exceeded every expectation. Daily operations now focus on careful power management and strategic decision-making about which instruments to keep active. Each remaining instrument provides unique insights into the interstellar environment, yet each consumes precious watts. The team has implemented innovations unimaginable when the spacecraft launched, including strategies that allow instruments to share power more efficiently and techniques that extract more information from each precious watt of transmitter power. They've learned to communicate with their aging explorer using less energy, adjusting data rates and compression algorithms to match the spacecraft's declining capabilities. The mission has provided insights that transformed scientific understanding of the outer solar system and the boundary where solar influence meets galactic space. Before Voyager, theories about the heliosphere and its extent remained largely speculative. Now, scientists work with actual data from beyond that boundary, measuring plasma densities, magnetic field characteristics, and particle populations in the local interstellar medium. This information helps calibrate models not just of our own stellar environment, but of how stars in general interact with the galactic medium in which they're embedded. Voyager 1 detected oscillations in plasma density that allowed scientists to calculate the density of the local interstellar medium directly for the first time. These measurements revealed that space between stars isn't as empty as once thought. containing roughly 0.1 particles per cubic centimeter, mostly hydrogen. While this still represents a vacuum far better than anything achievable in terrestrial laboratories, it's significantly denser than theories had predicted. This denser medium suggests that the solar wind's influence may not extend quite as far as earlier models calculated, and that the interaction between stellar winds and galactic medium might be more complex across the galaxy than simplified models suggested. The spacecraft also provided evidence for a bow shock or bow wave ahead of the heliosphere, though debate continues about the exact nature of this structure. As the solar system moves through the local interstellar medium at roughly 26 kilometers per second, it should create a shock wave similar to a boat moving through water or a supersonic aircraft through air. Voyager's data suggested such a structure exists, though follow-up analysis indicated the relationship between heliosphere and interstellar medium might be more complicated than simple shock models predict. These discoveries emerge from instruments designed and built decades ago by teams using technology that seems primitive by modern standards. The magnetometer aboard Voyager 1, for instance, uses flux gate sensors mounted on a boom extended from the spacecraft to minimize interference from the craft's own magnetic fields. This design dates to the early 1970s, yet it continues providing measurements accurate enough to detect subtle variations in the galactic magnetic field. The cosmic ray subsystem employs solid-state detectors that count individual particles as they strike silicon wafers, a straightforward approach that remains effective despite its age. Contemporary spacecraft designs benefit enormously from Voyager's experiences. Mission planners now better understand the long-term effects of space exposure on materials and electronics. They recognize the value of redundancy, of conservative engineering that builds in margins beyond calculated needs, of autonomous systems that can respond to contingencies without awaiting instructions across vast distances. They've learned that simplicity offers advantages, that elaborate systems introduce more failure modes, that robust design trumps clever optimization when dealing with missions that must function far longer and farther than anyone can guarantee. The philosophical implications of Voyager 1's journey resonate beyond its scientific contributions. This spacecraft embodies humanity's relationship with the unknown, our willingness to invest resources in questions that don't promise immediate practical returns. The mission cost roughly $865 million in 1977 dollars, roughly $4.2 billion adjusted for inflation. This investment bought knowledge about planets we'll never visit in person, about a boundary we'll never see with our own eyes, about space so distant that light needs a full day to cross the gulf between spacecraft and home. It bought something else as well, something harder to quantify, but perhaps more valuable. Proof that humans can conceive and execute projects that extend beyond individual lifetimes, that serve future generations, and that honor curiosity as a virtue worth supporting. Every child who learns about Voyager, one encounters this example of long-term thinking, of goals that transcend immediate gratification. The mission demonstrates that humanity can occasionally set aside short-term concerns to pursue understanding for its own sake, can cooperate across decades to maintain a project whose benefits accrue slowly and subtly, can find meaning in questions without guaranteed answers. These lessons matter now perhaps more than when the spacecraft launched, as humanity faces challenges that require exactly this kind of sustained, multi-generational commitment. The spacecraft's gradually dimming power and slowly failing systems mirror mortality itself. Like all explorers who venture too far from home, Voyager 1 will eventually fall silent, and its last transmission lost in the noise of a universe that hums with radiation across every wavelength. The specific year remains uncertain. Engineering estimates suggest the spacecraft might maintain enough power to operate at least one instrument until approximately 2025 to 2030. After that, the radioisotope generator will produce too little electricity to power even the transmitter, and the spacecraft will go dark, its computers perhaps continuing to run through programmed routines that no one will ever receive, executing instructions in isolation until cold or radiation finally ends even these automatic processes. When silence comes, Voyager 1 won't stop existing. It will continue along its trajectory, subject only to gravitational influences too subtle to significantly alter its path on timescales shorter than millions of years. It becomes a ghost ship sailing an ocean without shores, carrying its golden record and its silent instruments through the space between stars, a monument to a moment when one species on one planet decided that reaching beyond itself mattered enough to commit resources and imagination to the effort. Other civilizations, if they exist, must face similar choices. Any technological society that develops the means to explore beyond its home world must decide whether to do so, must weigh the costs against uncertain benefits, must choose between looking outward or focusing inward. Some may choose differently than we did. Some may decide that space is too vast, too hostile, too empty to warrant the effort. Some may possess curiosity in different forms, pursuing knowledge through means we wouldn't recognize. Some may have existed and disappeared long before humanity evolved, leaving no traces we could detect. Some may arise long after our own species has either transformed beyond recognition or vanished entirely. In this context, Voyager 1 serves as humanity's statement that we were here, that we asked questions and built machines to help answer them, that we possessed imagination sufficient to dream beyond our immediate circumstances. The spacecraft carries no weapons, makes no territorial claims, asserts no dominance. It simply explores and reports what it finds, offering information freely to anyone who cares to receive it. This stance reflects something essential about science as an enterprise. Its goal is understanding shared among all who seek it. Its ethic is honesty about uncertainty. Its spirit is humility before complexity. The engineers monitoring Voyager 1's status continue making decisions that squeeze additional weeks or months of operation from declining resources. They've shut down non-essential systems, adjusted communication protocols, revised command sequences to minimize power consumption. Each choice represents a small victory against entropy, a temporary assertion of function over decline. They know the end approaches inevitably, yet they work to postpone it, to gather every possible piece of data, to extend the mission as far as ingenuity allows. When the final signal arrives, when the last data packet makes its 22-hour journey home and no subsequent transmission follows, the mission team will wait longer than seems reasonable, hoping for an unexpected reprieve. They'll point the massive dishes of the deep space network toward that distant point where their explorer drifts, listening for signal in the noise, searching for any indication that power has been found somewhere, that one more message might cross the dark. Eventually, they'll accept that silence means ending, that their ancient explorer has finally exhausted its ability to communicate. There will be sadness in this recognition, tempered by satisfaction at a mission that far exceeded every expectation. Voyager 1 will outlive everyone who built it, everyone who operated it, everyone who learned from it. It will outlive their children and grandchildren, will outlive civilizations yet unborn, will persist through eras so distant that present human concerns will have faded to irrelevance or transformed into something unrecognizable. And through all those uncountable years, it will carry with it the golden record. Those images and sounds carefully selected to represent a species that briefly wondered if anyone else was listening, that hoped connection might span the dark, that believed its message worth sending even into silence.